All right, welcome back to The Explainer. Today, we're jumping right into something huge, the beautiful, complex, and, let's be honest, fundamental language of life itself, organic chemistry. We're going to break down the 24 core concepts, the real bedrock of the entire field.
But it all boils down to one single question. Just look around you for a second. Everything that's alive, it's all built from molecules based on one single element. So what is it? What gives carbon this incredible power to create the millions upon millions of molecules that make up life as we know it?
All right, so let's get into it. To even begin to answer that, our story has to start small. Really small. We've got to start with the atom itself and figure out what makes carbon the undisputed king of the elements.
So when we say organic chemistry, what are we really talking about? At its absolute core, it's the study of carbon. Think about that. An entire branch of science totally dedicated to this one element. And it's all because of how special it is.
And the answer to that big question from the beginning? It's one word: catenation. This is it. This is carbon's superpower. It's this unique, incredible ability to link up with itself, to basically hold hands with other carbon atoms, forming these super long, super stable chains, crazy branches, and even perfect rings. Seriously, no other element even comes close to doing this so well, and that is the foundation for pretty much all of life's complexity.
Okay, so carbon can form these amazing chains. Got it. But how do we get from a simple chain to the detailed molecular blueprints for everything? Let's dig into that next. See, carbon doesn't just build things randomly. It's way more organized than that. It creates these families of molecules called a homologous series. The best way to think about it is like building with Legos, right? Every member of the family uses the same basic brick, and you just make the structure longer by snapping on the same simple repeating piece over and over.
So if they're all built from the same repeating blocks, what gives each of these families its unique personality? Well, that would be the functional group. This is the key part. It's the active site of the molecule. You could call it the business end. It's what dictates exactly how that molecule is going to behave and react with everything else.
Okay, now this is where things get really, really cool. You can have two molecules with the exact same chemical formula, the same atoms, but they behave completely differently. We call these isomers. You've got structural isomers where the atoms are literally connected in a different order, and then you have stereoisomers which have the same connections, but they're just arranged differently in 3D space. The classic example is your left and right hand. They're mirror images, but they're not the same.
So what's actually holding all these atoms together? It's covalent bonds, and there are really two main types you need to know. First, you have the sigma bond. This is the strong one, the stable, head-on connection. It's like the steel frame of a building. It forms the skeleton of the molecule. Then you have the pi bond. This is a weaker, sideways overlap that you find in double and triple bonds. It kind of hangs out on the outside, which makes it more exposed and way more reactive.
But wait a minute. How does carbon manage to form all these different kinds of bonds and all these crazy shapes? Well, it's through a really neat process called hybridization. It's almost like carbon customizes its own toolkit for each job. It literally mixes and matches its standard atomic orbitals to create brand new specialized hybrid orbitals. And doing that allows it to get the exact angles and the exact geometries it needs to build everything from flat rings to these incredibly complex 3D molecules.
All right, so we've got the blueprints. We understand how the structures are put together. But if you really want to understand a molecule's personality, how it's actually going to act, you have to look deeper. You have to look at the invisible forces that are constantly at play, that unseen flow of its electrons.
When it comes to chemical reactions, you can basically think of it as a story with two main characters. On one side, you have the electrophile. It's electron poor, it's kind of hungry, and it is actively searching for electrons. And on the other side, you've got the nucleophile. It's electron rich, it has electrons to spare, and it's looking to donate a pair. Honestly, the dance between these two, that's what drives pretty much all of organic chemistry.
Now here's the thing, electrons aren't always shared fairly between atoms. And that brings us to the inductive effect. You can picture it as a permanent game of tug-of-war. If you have an atom that's more electron greedy, what chemists call electron negative, it's always going to be pulling those shared bonding electrons a little closer to itself. This creates a permanent, slight imbalance of charge all the way down the chain.
Okay, resonance. This is a huge concept for understanding why some molecules are so stable. Basically, instead of being stuck between just two atoms, certain electrons can get delocalized.
It's like they're smeared out over a whole bunch of atoms at once, and sharing the electronic load like that, it just makes the entire structure way, way more stable. It's a massive stabilizing force.
And on a similar note, you have hyperconjugation. You can kind of think of it as a more subtle cousin of resonance. It's another different type of electron sharing that acts like, well, like an extra dab of glue. It gives the molecule this little extra boost in stability that, trust me, can sometimes make all the difference in a reaction.
Now, in contrast to the effects we've just talked about, this next one is totally temporary. The electromeric effect only happens when another molecule gets close, when it's about to attack. The pi electrons in a double or triple bond will suddenly shift completely over to one atom, creating these temporary positive and negative charges. It basically primes the molecule, getting it ready for an immediate reaction.
Okay, so we've seen the blueprints. We've peeked behind the curtain at the invisible forces. Now it's time for the main event. How do these molecules actually interact with each other? We're going to look at the 4 fundamental types of reactions.
So it's important to know that reactions aren't always just A goes to B in one clean step. A lot of the time, they create these super unstable, very short-lived middlemen that we call reactive intermediates. There are 3 big ones you'll see all the time: the positively charged carbocation, the negatively charged carbanion, and the neutral, but extremely reactive, free radical.
First up, we've got the substitution reaction. And honestly, it's pretty much as simple as it sounds. It is a molecular swap. One atom or group on a molecule gets kicked out and replaced by a new one. That's it. Next on the list is the addition reaction. This one's all about coming together. You take 2 or more molecules, they combine, and you end up with one single larger product. And how does that happen? Usually, a relatively weak pi bond breaks, making room to form 2 new, much stronger sigma bonds.
And then we have the elimination reaction, which is, you guessed it, pretty much the exact opposite of an addition reaction. Here, you start with one large molecule, and a couple of atoms or groups are removed from it. The result? You form a new double or triple bond, and you spit out a smaller, separate molecule.
And finally, we have oxidation and reduction. These two are a pair, 2 sides of the same coin, really. In the world of organic chemistry, it often boils down to something simple. Oxidation usually means you're adding oxygen or removing hydrogen. And reduction, you just flip it. It's adding hydrogen or removing oxygen.
And that's the whole journey. Think about it. We started with the unique superpower of a single atom, carbon. Then we saw how those atoms get assembled into these incredible molecular blueprints, how the flow of their electrons gives them a unique personality, and finally, how they actually take part in the fundamental reactions that build and transform, well, our entire world.
So, everything we've just gone over, these are the fundamental rules of the game. These are the principles that govern how the molecules of life are built and how they interact. Which leaves us with just one final, pretty provocative thought. What happens when we learn to break those rules?